All right, to have these 5 problems to talk through for related rates. So some of them I'm just going to get you set up and kind of go fast, but the work is all there scanned into Schoology. And of course there's PLT, and you can come in to see your teacher if you're still feeling stuck. But I think the setups are where most of you are feeling a little lost. So at a sand and gravel plant, sand is falling off of a conveyor onto a conical pile. So conical meaning cone. At a rate of 10 cubic feet per minute. Well, 10 cubic feet per minute would indicate volume dt, because cubic feet measures volume and minutes measures time. The diameter of the base is approximately 3 times, I'm going to call this the altitude, the height. At what rate is the height of the pile changing? So dh dt equals question mark later when h equals 15 feet. So that's pulling out all of the important information. Hint, the formula for the volume of a cone is volume equals 1/3 pi r squared h. Yes, you should be aware of that formula. Next thing then, I need to think about what I have versus what I want. So I know some information about volume. I want to know some information about height. So great, this equation relates volume and height, except I have this other pesky r in the way. Well, what can I do to get r? The diameter from geometry is twice the radius of the circle. So twice the radius is equal to 3 times the height, which means the radius is equal to 3/2 of the height. So now, if I go, I'm going to use a little fancy pen. If I go to do my volume again, I can say this is equal to 1/3 pi, and I can replace my r with 3/2 h squared, all of that times h. Cleaning this up more, I get volume equals 1/3 pi 9/4 h to the second times h, which is h to the third. Now I have an equation that relates just volume and just height, so I can take the derivative with respect to time. One last step I would suggest doing is saying 9 divided by 3 is 3. You don't have to, but it might make things a little bit easier. And now I'm ready to take the derivative with respect to time. I've now related my variables, so now I'm going to relate their rates. dv dt equals 3/4 pi is a constant, it just hangs out. The derivative of h to the third with respect to time is 3h squared dh dt. It is now later. Okay, and you related your variables, now you've related their rates. Now you get to plug in all of your information. So dv dt, according to the information that was provided, was equal to 10 cubic centimeters. 3 and 3 makes 9/4 pi. Because it's later, h is 15, square it becomes 225, and dh dt is my mystery. Now, if you have your calculator, yes, you can divide over if you're very, very careful, and you can come up with the answer of 0.00629. But if you're not so careful with your calculator, things are going to go awry, which is where I suggest we just use a little bit of math and just go slow. So if I multiply over by 4/9, I'm going to get 40 over 9 is equal to 225 pi dh dt. So then I'm going to divide, which is the same thing as multiplying by the reciprocal. And then, thinking about what they have in common, that's a 225, by the way, I end up with 8 over 405 pi. This is going to be in feet per minute because we're talking about dh, and h would be measured in feet. dt, time is measured in minutes. If you were to put this in your calculator, you would need to type in 8 over 405 pi. And that's where I get that 0.00629 feet per minute. Okay? So the key there is only relate the variables that you care about. You only care about volume and height. You don't care about the radius, so you want to ditch it and get it in terms of height first. If you're stuck on that one, there should have been one like it in the Turvey, which I think Mr. Lakin made a video about. So, number 18, the volume of oil in a cylindrical container. Well, cylindrical container would imply that we are talking about a cylinder. Is increasing at a rate of 150 cubic inches per second. So the volume is increasing, so positive 150 cubic inches per second. The height, so that's from this part, the height of the cylinder is approximately 10 times the radius. So we'll put a height here, put a radius here. At what rate is the height of the oil changing when the oil is 35 inches high? So later, when H equals 35 inches. Hint, the volume is pi r squared H. Okay, great. I have volume stuff. I've got H stuff. This equation has those two, except I have this, again, pesky r in the way. Well, I know that H is equal to 10r, which means that r is equal to 1/10 of H. So volume equals pi. I'm going to replace that r with 1/10 H. Volume then ends up being equal to pi over 100 H cubed. I'm going to take the derivative with respect to time, because my variables were related the way I needed them to be with just volume and just height. So I get dv dt equals 3 pi over 100 H squared dh dt. Now, because I've taken the derivative, it's officially later. And I can substitute in all of my different things. I'm looking for dh dt is what I was hoping to solve for. And we end up with dh dt is equal to 200 over 49 pi inches per second. Because again, H is measured in inches, time is measured in seconds for this problem. All right, moving along. Oh, my pictures got a little messed up here. So we have our ladder problem. We did a ladder problem in the one that Mrs. Lemke and I made, so you can look back at that one for part A. I'm assuming that people were mostly concerned about B and C, so I'm going to go with part B and pick up there. Consider the triangle, the ladder, and the ground. Find the rate at which the area of the triangle, area equals 1/2 base times height, is changing. So dA dt equals question mark. Later, when the base, so I'm just going to call this B for base, later when B equals 7 feet. All right, so in this situation, I don't really have a way to get stuff in terms of just B's. I mean, you could if you were really savvy with the Pythagorean theorem, but you have information about about R, I guess in our case, get it? So you could use what's information here, right? The base of a ladder is being pulled away at 2 feet per second. How fast is the top of the ladder moving down the wall at 7? So we already did that in part A. And in part A, we came up with -7/12 feet per second was equal to dr dt. So I have stuff about dr dt. I have stuff about dB dt. I can just take the derivative right here with respect to time. So I'm going to end up with dA dt equals 1/2 is just going to hang out in front. First times the derivative of the second plus the second times the derivative of the first. Now, because I took the derivative, it's later. So how fast is the area changing? That's what I would like to know. Later, when B is 7, dr dt we found from before was -7 twelfths, I believe. And then plus 24 because of the 7, 24, 25 triangle times, we knew this rate, what did it say? 2 feet per second. And you can clean that all up because we're talking about the rate of change of an area. We are going to use our units of feet squared. So I came up with 527, if my pen will let me write. 527, that's me writing with my finger, not great, over 24. Area, again, is measured in feet squared per second. If you are stuck on part C, okay, part C is going to be a lot like the lighthouse problem that we did. I'm just going to get it set up for you, and then you'll use trigonometry. If you haven't watched the video about the lighthouse, you might want to look back. Mr. Lakin made one. If you were in my class, you saw me do that problem live, so you could look back at your notes. But it says, find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet away. So, oh, that should be my later moment. So I need to relate theta and B for base. So what relates theta, B, and 25? That's going to be the sine of theta. That's a theta, equals B over 25. And I am looking for d theta dt equals question mark. Later, when B equals 7 again. Okay, so I'm ready. I have theta. I've got information about dB dt being 2, so I can take the derivative of this with respect to time. The derivative of sine is cosine, leave theta alone, times the derivative of theta, the inside, with respect to time. This one, instead of thinking about this as b over 25, I'm going to think mathematically as 1/25th b. So this will become 1/25th dB dt. So now, it's the moment we've all been waiting for. It's later, when b is 7, we've got theta up here. The ladder is still 25. This now becomes 24 because of our triples in geometry. So cosine of theta is going to be 24 over 25, adjacent over hypotenuse. Then, from there, d theta dt is what we want to find, equals 1/25th, and then dB dt was 2. So solving for d theta dt, you're going to end up with 1/12 radians per second. And I realized, here, d theta, that's terrible. D theta dt, theta is measured in radians. I realized in my answer key from my work, I think I might have answered the wrong problem when I first made my key. Find the rate at which the angle between the ladder and the wall is changing. So this is what we want, this setup. If that's what confused you, I should have been using sine. However, if you think about how angles relate to each other, so that angle is getting bigger, right? And if we think about our angle down in the other side, right? If this was our other, we'll call it beta, I found how d beta dt, I found how beta was changing. So I apologize for that if that was confusing, but that's the type of thing. Hopefully you can check in with your teacher if you need to. Also, again, look over that lighthouse problem. The lighthouse will guide you. Get it? That's what lighthouses do, people. All right, I'm going to make one more really quick video to finish these out, and then I'm going to go make dinner. Bye.